little bit of review of the two trig equations that I told you guys to memorize. So you guys do have a quiz in your near future, very near future, not today, but soon. And there were two trig things in the notes that I told you guys to memorize. So if you remember, the first one was the limit as x goes to 0 of sine of x over x. Do you guys remember what that goes to?
1.
1, perfect. And then the other one is the limit as x goes to 0 of 1 minus cosine of x over x. And that goes to? 0. Good. So those are the two that you definitely need to know for the quiz. So all of these, well, most of these, are going to be variations of those two. So on number 1, when you look at it, we have sine of x times 1 minus cosine of x over 2x squared. So what we can do with limits is we can kind of break them apart. So we can say, well, this is the same as limit as x goes to 0 of sine of x over x and 1 minus cosine of x over x. And then I just have an additional what? 1 over 2, right? So I'm breaking it apart. And we know limits that I can take this limit as x goes to 0 into each individual piece of the product, right? So I could take the limit as x goes to 0 into each thing. So what does sine of x over x go to? 1. So sometimes we draw a little arrow through it and then put 1. What does 1 minus cosine of x over x go to? 0. So we end up getting 1 times 0 times 1/2, which is still 0, exactly. So it's 0. Okay, so number 2, I do think that we possibly have done before. So we're going to write our cosine of theta, and then our tangent of theta is sine of theta over cosine of theta. So luckily those cosine of thetas will go away, right? So cosine theta divided by cosine theta, it's gone. So we end up getting what we want. We get the limit as theta goes to 0 of sine of theta over theta. So it doesn't matter that I have thetas. I feel like thetas cause people anxiety sometimes. They're like, why is there a theta in the problem? You're fine. You're past pre-calc. You got theta. You understand that it's just a variable, right? So just like x. So this is all going to go to 1 then. So we got it. All right, so the next one. So it's a little tricky. So first we can kind of think about what secant is. Well, secant is 1 over cosine, right? So we have the limit as theta goes to 0, or it goes to pi of theta over cosine of theta. What do you think we do? You just plug in pi, that's it. So sometimes people like overcomplicate things, especially there is one, wink, wink, on your limits quiz that some of you guys are probably going to factor and try to do things with, and then you're going to realize, oh wait, I can just plug in the number. Like sometimes that happens where like if I had like an x minus 3 on the bottom and I was saying the limit as x went to 4, like that doesn't make it undefined, right? We can just plug it in. So look for things like that. So in this case, we can plug in pi. So when we do, we get pi over cosine of pi. And cosine of pi is -1. So we get negative pi. Still feeling good about these? All right, so how about this next one? So we're going to break it apart again. So we have the limit as h goes to 0, and we have 1 minus cosine of h over h like we want. But then we have an additional 1 minus cosine of h, which is fine. You can put it over 1 if you want to, it doesn't matter. But if you remember, we know that this part will go to 0 as h goes to 0, right? So be careful, it's not as h goes to pi or anything, right? H has to go to 0. So we do get 0 there, and even if this other part didn't go to 0, like when I plug in cosine of 0, I do get 1. So I get 1 minus 1, which is also 0. But even if it wasn't, we would have 0 times something, so it'd still be 0. Usually that 1 minus cosine of h is kind of a red flag that you're probably going to get 0. All right, so
Why is it at the second?
Why is it what?
Why is it at the second?
Because it's 1 minus cosine of 0, and cosine of 0 on your unit circle is right there, so it'd be 1.
That's where you would plug in 0.
Yeah, you would just plug in the number, yeah. All right, so this next one is almost like the sine of x over x, but it's the sine of x over the cube root of x. I know, it's weird.
So you have to bring the cube up.
What do you mean by that? Oh, yeah, so I'm trying to get it so it's just plain x on the bottom. It's like I'm trying to rationalize the denominator. What if I want to get a root out of the denominator? Is it the same thing? So if I multiply by root x, don't I get the cube root of x squared? Does that work? So how many x's do I need under a cube root in order to just get x? I need 3, so I need 2 more. So it's like this is really x to the 1/3. And if we want to multiply by something so that the powers add to be 1, it would need to be 2/3. Does it make sense? Kind of tricky. So we're going to do the cube root of x squared. So then we do have the limit as x goes to 0, and we have the sine of x over x, but we have this additional cube root of x squared. Do you guys see that? So like all of this right here combined to be just plain x, cube root of x cubed, which is x. Seeing a lot of blank stares. Say, yes, Mrs. Cox, we get it. We're good. All right, so what do we think? This part goes to 1, right? This part is 0. So it's all equal to 0. Do we know the next one, number 6? It is 3/2, correct. Yes, I probably did. Oh, what if, I should probably add another one. I'm going to add a number 9 over here. What if I have the limit as x goes to infinity of sine of x squared over 5x? What do you think? Or even, let's not do sine of x squared. What if I did sine of 7x over 5x? What do you guys think? Oh, I tricked you! All of you fell for it too. Like Phil was so excited. 7/5, it's a trick. Nick remembered, okay. So this is where it's x goes to infinity. So be careful. The AP test has been tricky like that too. So as x goes to infinity, this part gets huge, right? This is a big number. This part is at most 1. So if I have 1 over a huge number, yep, it goes to 0. All right, and then the last two that we're going to talk about, I used to have these in the notes, and I guess I removed them over the years, but I like them. So let's kind of think about a t-table for this. So I want you to plug in numbers that are on the right and left of 5. So you can plug in 5 as well if you want to. So try like 4 and 3, maybe 6 and 7 as well, and 5. Let's see what you get for each one. So I'll give you a second to think about it. All right, who thinks they know what the graph looks like? All right, so numbers bigger than 5, like 6 and 7, what do we get? 1, yeah, you got a 1 for those, right? So anything that's bigger than 5 is going to be at a height of 1, except at 5. We don't know what's happening at 5, right? It's undefined. Anything smaller than 5, when I plug in 3, I get -1, right? So -1, -1. So it looks like this. So there was a mathematician who once came up with this type of function. It's not exactly like this, his function that's named after him. His name was Heaviside. That was his last name. Isn't that kind of funny? Because it's like a heavy side. I don't know. I don't know. Was he heavy? I don't know. But that was his name, Heaviside. So this is, so what do we think? So the limit as x goes to 5 in general, it does not exist because as we trace from the left and the right, they go, the right side goes to 1, but the left side goes to -1. So this would be d and e. But what if I had 5 from the left? What would I put? -1, exactly. And 5 from the right? 1, exactly. All right, so let's do the next one. So this is the same idea, right? So for values, whoops, -2. So values bigger than -2, we get 1. Smaller than -2, we get -1. So as I'm approaching from the left-hand side, it goes to -1. All right, does that make sense? Do you guys feel pretty good about this?